Until now, ultrasounds have been used profoundly for diagnosing complications throughout the human body. Recently, scientists have discovered that ultrasounds can be utilized in more ways than just diagnosing conditions, but can actually be used to help treat certain diseases. High-intensity focused ultrasounds will be the future of medicine, as it could help fight cancer in ways that have not been discovered. So you might be wondering how a simple sound wave can produce an image. You might also wonder how a sound wave can produce real-time motion photographs, and most importantly, how is it possible to treat cancer? Let's talk about it. Before we get into the real physics behind ultrasounds, let's talk about what an ultrasound really is. In other words, ultrasounds can also be called sonography. Ultrasounds is an imaging technique used by doctors that help visualize the internal tissues of the body. How does it really work, you may ask? It uses high-frequency sound waves to produce images of organs and tissues within the body. The frequency goes up to 2 MHz to 15 MHz, which is way higher than the upper audible limit of human hearing. If you've gotten an ultrasound before, you know that a magic wand is placed on your body. This wand is actually called a transducer, and that probe creates the image that you see. Now, since we know a little bit more about ultrasounds, where did it come from and who invented it? A very long time ago in Paris in 1880, Pierre Curie and Paul Jacques Curie were experimenting with crystals when they discovered the piezoelectric effect. To summarize the piezoelectric effect, it is the occurrence of sound waves when energy is applied to the material. These materials were specifically quartz crystals and ceramic crystals. The piezoelectric materials were discovered accidentally by Paul Levine. Paul did not stop there though. He then later discovered that these piezoelectric materials can generate and receive mechanical vibrations with very high frequencies. And in 1920, he discovered that ultrasounds can produce heat in bones and tissues, which allowed Carl and Frederick Dusick to use ultrasounds as a medical device to diagnose and visualize tissues and bones. Isn't that crazy? Soon after, ultrasounds became a fundamental device used in the medical industry, and it still is today. Why ultrasounds, you may ask? Well, ultrasounds are a magnificent device that is used universally to examine multiple conditions. The most common example is when a woman is pregnant. They get an ultrasound test to see if their baby is strong and healthy. Not only is it used to observe babies, but it's also used to look at blood flow, diagnose gallbladder disease, and cancers, and the list can go on. As you know, our body is not a 2D object. We are all different sizes and shapes, and our organs and tissues are also different densities. Like I said previously, the ultrasound frequencies can range up to 2 MHz to 15 MHz, and the frequency determines how far the waves can penetrate the tissue. The higher the frequency gets, the shorter the wavelengths, and the shorter the wavelengths, it means that it's more easily absorbed by the body. This is actually very important when it comes to examining a patient. Let's say a person walks in and has a deep abdominal wound. What would you use? Let's break it down. So we know that it is a deep wound, meaning that it's not near the surface of the body. Knowing that higher frequencies are less penetrating than lower ones, which frequency would you use? 2 MHz, 6 MHz, or 15 MHz? Yes, you would use a 2 MHz one because it's more penetrating and the sound waves are not being absorbed as much, allowing you to get a good visual of the wound. As you may know, ultrasounds are connected to an electrical source. You may wonder how that creates sound waves. Let's take a look. To recap, the piezoelectric effect is when an electric charge is applied to a series of piezoelectric materials, which then produces sound waves. This can also work the other way as well. Let's take a look at a very simplified quartz crystal. A quartz crystal is made up of silicon dioxide. We know that silicon has a partial polar positive charge while oxygen has a partial polar negative charge. If we were to look at this bond at a molecular level, this will be the simplified model of a quartz crystal. You can see that it is geometrically symmetrical. There are 3 partial positives and 3 partial negatives, but are distributed evenly, making the overall effect on the crystal neutral. Now, what do you think will happen to the lattice of the bond if a compression force is applied? Let's try it. When a compression force is applied onto the bond, the lattice of the substance gets distorted so that it creates a positive and negative end, as you can see here. Since the substance is now not neutral, it has a positive and negative end, creating a very small electric field, which allows current to flow. Since the top is positive, the current will flow down to the negative side, meaning the current will flow down the page. Now, if you were to do the opposite of compressing the crystal, almost applying a tension force, what do you think will happen? Similar to the compression force, the tension force distorts the crystal the other way like this, making one end more positive and the other one more negative, again generating an electrical field. What could you now say about the flow of the current? It will go out of the page. Since the bottom is now positive and the top is negative, it'd be the opposite of what occurred before, so that the current would come out of the page. Now, if you were to keep alternating the compression and tension forces, you can generate an alternating field, which leads to an alternating current. So, when sound waves hit the crystal, that's what occurs. The crystal vibrates back and forth, alternating the electrical fields, allowing the mechanical energy to be converted into electrical energy. Doing the opposite now, if you were to apply a current or an electrical signal onto the crystal, it would vibrate the same way as before, creating an alternating field, but instead of turning it into electrical energy, it turns into mechanical energy, or in other words, sound waves. Now applying this to ultrasounds, the transducer actually consists of a large array of these piezoelectric crystals. And since it has a source of electrical energy, the crystals can now produce high-frequency waves. To be a little more specific, only every other crystal is hit with electrical energy, so that when the ultrasound waves are reflected back, the other crystals can transform these sound waves back into electrical energy. To create an ultrasound image, an electrical signal is applied to the transducer emitting high-frequency sound waves. Once the waves hit different characteristics and densities of tissues, the waves are reflected back to transducer, which are then converted back into an electrical signal once it hits the transducer. It then produces points of brightness on an image showing how strong or dense the tissue or structure is. There are three types of ultrasounds: A mode, B mode, and M mode. A mode ultrasounds consist of an X and Y axes. The X axis tells you the depth and the Y axis tells you the amplitude. B mode is based on brightness and is dependent on the amplitude or intensity of the echo. M mode is for motion mode. It's a one-cycle motion image, almost like a GIF, and is created by recording the amplitude and rate of motion in real time. Now, how do ultrasound waves travel? Wave propagation is the way a wave travels with respect to the direction of the oscillation relative to the propagation direction. In other words, basically the transmission of motion. There are two types of waves, longitudinal and transverse. In transverse waves, the particles in the wave move perpendicular to the direction of the wave, and in longitudinal waves, particles move with the direction of the wave. Waves propagate slower in a less dense medium like gas because the particles are very widely spread. When the sound hits a particle, it takes a longer period of time for it to hit the neighboring particle, causing a slow propagation. Whereas in solids or liquids, the particles are closer, allowing the wave to travel faster as they can bump into one another quicker. An ultrasound uses longitudinal waves and the particles of the medium to oscillate along the wave propagation axis. Let's take a closer look to what that means. Here I have a spring which can represent the sound waves. If I were to tap one end of the spring, you can see that the vibration travels all the way down onto the other side of the spring. Like a longitudinal wave, the spring loops move back and forth but not really losing their actual position. Take a closer look at the spring. You can see that the spring bumps into one another all the way down, creating areas that are closer together and some that are further apart. This is called compression and rarefaction. The actual particle itself does not move. It bumps into its neighboring particle and transfers the energy onto the other particle. You may have heard of high-intensity focused ultrasounds before, but have you really thought about what it actually means? As we know, ultrasound imaging and treatments are non-invasive to the body, meaning there are no incisions made to accomplish a task. The task is simply performed by the transducer. Like an ultrasound, high-intensity focused ultrasounds is a non-invasive technique which can be used for cosmetic reasons, like tightening the skin, and most importantly, it can be used to destroy unwanted and harmful tissues in the body, like tumors. Similarly to ultrasounds, high-intensity focused ultrasounds uses non-ionizing ultrasonic waves to help heat up the tissues. In order to do that, the ultrasound has a fixed focus on the target tissue it wants to implode. Ultrasounds that are used for sonography have a fixed focus, meaning that the focal point cannot be synthetically produced. In a transducer, the focal point is usually determined by the style of lens in front of the piezoelectric crystals. For the transducers to create a focal point, a concave lens is put in front of the array of crystals so that when the ultrasound beam is transmitted, it produces a fixed focal point. Although this is a new technique, researchers have already applied it to help fight prostate cancer in men. High-intensity focused ultrasound waves actually heat up the unwanted tissue to higher than 90 degrees Fahrenheit, intentionally burning the borders of the tumor and the rest of the cancerous tissue. This technique to help prostate cancer patients has been done before and has been very successful. Similar to the previous technique, there are clinical trials being performed to see how high-intensity focused ultrasounds can be used to help treat brain tumors. Since ultrasounds is a non-invasive technique, it could potentially improve the patient's quality of life. How this high-intensity focused ultrasound works for brain tumors is that there's a machine equivalent to a CT scan, but before you go in, your head is placed in a helmet-looking like object. In this helmet, there are a bunch of transducers that are positioned all around the helmet and emit high-energy sound waves to where the tumor is. Since there are so many sound waves targeting one point from all different angles, the tissue can get really hot, up to 100 degrees Fahrenheit in 20 seconds. This will happen in sections until the unwanted tissue is destroyed. This technique is still being tested as there could be side effects, but this procedure is non-invasive. Since there are no incisions being made, there's a great decrease in chances of getting blood clots and infections and tissue damage. Since the sound waves are so focused and precise, there is no damage done to the surrounding tissues. And that, everyone, is how a simple sound wave can help destroy tumors. We applied how ultrasounds are beneficial to society and how the technological devices work, but how can it be used in other situations, like for the environment? As we know, ultrasounds create no toxic chemicals nor emit no type of pollution into the atmosphere. It's also very cheap and portable. This can be very beneficial for the environment. For instance, recent studies have shown that ultrasounds can be used to treat water and sludge. It's known to treat organic contamination and infections in the water which are caused by the change in temperature. It can also be used for air purification. As high-intensity sound waves are emitted into the atmosphere, the unwanted particles agglomerate together, purifying the air. Lastly, it can be used to remediate soil as it removes metal scrap pieces and decontaminates organics. High-intensity focused ultrasounds is an amazing technique as it can perform outstanding tasks. Although it's not officially approved by the FDA, this procedure has a lot of potential to society and the environment. I hope you enjoyed my video and learned something new today. Thank you for watching and I will see you soon. Bye!